Now we're going to look at how the Tomasulo style of doing out-of-order pipelines, how it's implemented in modern processors of today. This is a picture that is fairly looks fairly similar for most processors implemented today. We often talk about different sort of stages, pipeline stages, with names like fetch, decode, rename, often in exactly that order. Then comes a large stage here, which is called the issue stage. Then it's a stage called the execute stage. Here is the write back stage, and then we have a stage called the commit stage. So typically 7 stages. Each of these stages may take several cycles to execute. So this is not a 7 cycle from beginning to end here. It's more like a 20 cycles from the beginning to end, even in the best case. So an instruction can also be stalled at several of these stages and sit and wait there. And sometimes instructions are split up and go to several boxes at the same time. Also, sometimes instruction may have to be restarted. So we have the rollbacks. For example, when there is a branch misprediction, there could be a need for rollback. But there are other situations where you will have to do a rollback as well. Commonly, these stages here are referred to as the front-end stages, and the rest of the stages are called the back-end stages. Maybe I should also point out here some of these boxes. So we have the instruction cache sitting here, that's attached to the fetch stage. We have a queue called the issue queue, where instructions go through the issue queue on their way to the execution unit, the ALUs here. We have something called physical registers. We have the dcache that you should recognize, and then we have another new box here called load store queue. And here up at the top is our friend, the reorder buffer. And in the reorder buffer, we have a head pointer and a tail pointer, so we know which is the oldest instruction and which is the newest instruction in the reorder buffer. Okay, so let's look at the fetch stage and discuss a little what's going on here. So during the fetch stage, we fetch some number of instructions, the width, fetch width here, some number of instructions, typically 4 instructions or so these days, each cycle. And in order for us to do that, we have lots of, take help from lots of functionalities that we already discussed in this course. So in the fetch stage, that's where the branch predictor is. So depending on what the current PC is, you're going to do lookup in the branch predictor and figure out whether this branch should be taken or not. We can also have the branch target buffer that stores the instruction we're jumping to in case the branch is taken. Return address stack, that was one that had to do with function calls when you're returning from function calls. And we also calculate a next sequential address. So all these 4 boxes here sit inside the fetch stage. They all help us to figure out what the next PC should be using some kind of prediction. And the logic for implementing this is quite complex. Good branch predictor is a very, very complex design these days. If there's a branch mispredict, it will take at least, I would say, 10 cycles before you find out that the branch that the outcome of the branch is not what you guessed. So you will miss 10 cycles, and during those 10 cycles you would have started 4 instructions per cycle, so you could start up to 40 instructions. So that's how many instructions that you have to squash before you know if the branch is taken or not. But also sometimes it could take even longer time. So if the branch depends on load value, load miss, so you have to fetch some value from memory, and that's what your branch depends on. The branch mispredict, you may actually find out maybe after 200 cycles that you made the wrong guess. So you would potentially have wasted 800 instructions by that mispredict. So it's important with good prediction. You fetch instructions in blocks, so you don't just fetch one instruction. You try to fetch more instructions at the same time, of course, because you want to start 4 instructions every cycle, or so. Actually, the width can be even higher, even bigger for some modern processors. Some of them start 6 or even 8 instructions each cycle. So your help, you have some hardware prefetching that figures out which instruction to fetch next. And you may also have something called a trace cache. So a trace cache is a cache where you store instructions in an execution order that you've seen before. So if there is a branch that often is taken, then the instruction before the branch, followed by the branch, followed by the instruction after the branch, they will sit together in this trace cache. So it's sort of a trace of the execution. That also makes the fetching job much simpler. And as already said, there's some fetch width, so typically 4 instructions or so are started each cycle. So this complex is just a little red box here, but it's lots of the complexity that you may appreciate from the earlier lectures that goes into that box. The decode is a little simpler box. So the decode has to deal with things like variable instruction length for x86 architectures, for example. So it's not really trivial to figure out, what the different bits of an instruction, what they mean. First, you have to figure out how long the instruction is, and that really depends on what instruction type it is. So it's sort of a sequential job. You have to figure out how long one instruction is before you can figure out where the next instruction starts, and so on. So it's the decode is tedious work as well. And also the decode typically is the box that makes translations from x86 instructions to micro-ops. Micro-ops are the instructions actually executed by the hardware, while the x86 instructions are the old kind of instructions that was defined many years ago, and some of them do not lend themselves to efficient implementations in this kind of architecture. So there is a translation going on. So one x86 instruction may be translated into 2 or 3 or so micro-ops, and so instead you have to execute all those 3 instructions in sequence. And you also identify the source and destination register, because that is something which is going to be needed by the next stage here. So the next stage is the rename stage. So in the rename stage, you allocate a physical destination register. So in the physical register file, and I keep emphasizing physical here, the physical destination file, you allocate the register. So you say from this instruction executed here, its destination register is going to be exactly that register over there. And then you update a translation table to remember what rename you did. So this translation table is a table that translates from architecture registers, the registers you would read about in the manual about the instruction set architecture, and some number of physical registers that are sit in the register file. So in this example, we renamed architecture the register 3, which was the destination register for this, to some specific newly allocated register, physical register that I call register X. The physical register file is much larger than the number of architecture registers. It can be an order of magnitude larger than the number of registers you have in the architecture register. So then, you update the translation table, then you rename your source registers as well. Because if source register, architecture register 1, it should be translated to physical register 4, and another source register is register 4, it should be translated to physical register 98, because those registers have earlier been renamed. So you also, at this point in time in the rename stage, may decide to take a checkpoint of this translation table. Especially if you execute a branch instruction that you know has a low confidence, so you know the branch predictions for this instruction has typically not been that successful in the past, then just to speed things up, you may take a snapshot of the entire translation table here. When it's not that many entries, if you have 16 architecture registers, there are just 16 entries in this table. Problem though is that you will start 4 instructions at the same time. So this renaming will take place for 8 source registers and 4 destination registers. if the width is 4. Okay, so it's quite a lot of work there as well. Then life goes on. We come to the issue stage. So in the issue stage, several things will happen. So we will put the instruction will be put in the reorder buffer, the issue queue, and the load store queue. So see how I abbreviate this to be ROB, IQ, and LSQ. Okay. So as I said before, so the instructions will go into the reorder buffer in program order because there is no reordering going on here. And we will put the newest instruction at the tail pointer in the reorder buffer. We will put the instruction in the issue queue on its way to the execution units. And it will sit and wait in the issue queue until its source physical registers are ready. So there is a very costly wake-up mechanism here. So there could be, 4 registers can be written each cycle, and those 4 registers can have a large number of instructions waiting for them. And we have to instantly find all the waiting instructions that have been enabled for execution. So we're not going to go through the implementation in detail, but you can imagine it's a very associative lookup all the time, every cycle. When you finish off write values to new physical registers, you have to figure out if somebody's waiting on those physical registers. The wake up is complex, but also can take quite a lot of time. So from the time you get a wake up signal here until this instruction is actually executing could be sort of like 4 cycles. So there's a big gap here. And so the whole issue queue here will do the wake up. It will also do scheduling of instructions. So if many instructions wake up in the same cycle, the scheduling have to decide which instructions to execute next, and that of course depends on which execution units are available. But it could also depend on other things, for example, age. So typically you prioritize the oldest instruction that's been waiting here the longest to be executed first if you have a choice. Also, you do quite an aggressive read after write scheduling. So I said from wake up until you start executing is 4 cycles. So right after an instruction has woken up and it's on its way to produce its result, then the very next cycle we wake up its dependent instructions. Even though the register is not available just yet, we know it will be available just in time when the register value is needed. So we do some kind of early wake up there as well. So it's complexity big time down here in the issue queue. And then you have the load store queue. So in the load store queue you have of course loads and stores sitting there, and what you check for is if there is some if some loads and stores are actually for the same address. And that's something which you can't statically figure that one out, because you have to calculate the address before you can figure out if there is some kind of dependence between those instructions. And of course, if load and stores start to bypass each other, it's really important that you catch situations where the loads and stores are for the same address. So a store should not be able to bypass a load, for example, and write a new value to the memory so the load will return the new value. That should not be possible. So that kind of thing. Also, the load store queue is involved in coherence activities. So if you have a load, if you've started the load long time ago, so you have already loaded the value from the cache, and now that cache line is invalidated, well, guess what? That entry in the load store queue also will have to be invalidated, because we cannot trust that data anymore. So it's there is coupling straight into the coherence as well here. Okay, then we have the wake up happens. So the source becomes available. So we have this sort of wake up mechanism. And as I said before, it takes 4 cycles, and you do an early wake up, as I said, because dependent instruction may be scheduled to be issued the very next cycle after the instruction that they depend on, because we can bank on the fact that the result will be produced in time. However, if the instruction you depend on is a load instruction, you don't know whether that load will hit in the cache or not, but you still speculate that it will hit in the cache. So typically, those instructions that are dependent on load instructions are issued as close in time as they can, so they can get so they are ready to execute exactly when the load returned the result. However, if it's a L1 cache miss, or if there is like a bank conflict or something going on, that means that when the dependent instruction comes to the ALU, the value they depend on is not available yet. What we'll do then, typically, is, well, a couple of solutions. One is to stall the ALU until the value becomes available, but that could take a long time. You can tie up in the ALU for a long time. Instead, you have some kind of mechanisms, so that is called a replay mechanism. So an instruction that was sent to the ALU for which one of the source values is not available may have to be taken out here and put back in the issue queue again and woken up at a later point in time. So it's called replay or selective replay, that kind of mechanism. The register file, since assuming now we're executing 4 instructions, so the register file is heavily multi-ported, and that makes it fairly expensive to implement. So lots and lots of physical registers, and you can simultaneously read 8 source and write to 4 destination registers at the same time. So it's, from a complexity standpoint, this is quite costly as well. Okay, then we come to the execute stage, and it's not much to say about that. That's probably the most simplest stage you can imagine, because you just make sure you get the register value that's available, and you execute, you multiply or add or whatever you do, and output the result. Then comes the write back phase. So in the write back phase, you update the location in the destination register in the physical register. So now it's updated, which may cause new wake-ups to be sent to the issue queue if anybody's waiting for that. You possibly could put, if this is a store operation being performed, you can put the data so it's ready to go here in the load store queue. On commit, so you do commit when the instruction is at the head of the ROB. So what you do then is free up lots of resources. You free up some physical registers. I'm not going to go in detail exactly what algorithm is going on, but typically each instruction that has a destination register, which is pretty much all instructions except for stores and branches. So all instructions with a destination register will free up a register, but not actually its own physical register. It's a little more complicated than that, but let's leave that for some other time. So we do that. We free up that. Then we, as I said, we could put, at this point in time is when we like to perform the store, because the stores has to be performed in order. The store is a side effect that's going to be seen outside of this core, because outside of this instruction, because we're going to store to the data cache. So this is a side effect that we cannot undo. So, and that has to be done in order. So we perform the store at commit as well. And they also have to make sure that the load data of one of these loads that we performed earlier has not gone stale. In other words, has not been invalidated by the cache coherence protocol. Because if that has happened, then we have to push the panic button and make sure that we unroll and redo part of the execution. And then we update the head of the RB of the RB pointer, so it's going to be updated to point to the other side of the instruction, and now we actually have committed this instruction. There are lots of situations where we need to do rollbacks. We already discussed if there's a branch misprediction, we will have to do rollback. We can't commit that branch. That rollback may happen first when the branch is at the head of the queue, or in some implementations it happens as soon as we know that the outcome is different from our guess. It really depends on complexity, exactly what you implement. Also, as I said, stale load data, they also will force you to do rollbacks, and there are lots of different exceptions that may force you to do rollback. For example, if you have a TLD miss, that is handled by a software mechanism. Then you have to have a precise exception so you can handle that TLB miss, which means you will squash all instructions that were started right after this instruction and take it the precise exception. So this is, as I said, it is a common way to implement processors these days. So the sizes of these different boxes here, I already discussed with an issue width of 4. Sometimes the issue width is different for different parts of the design. So you could have a different issue width here in the front end and from the back end, for example, to cover some specific corner cases and be able to restart the pipeline faster after a rollback, for example. So that's better. 4 is a common size. Reorder buffer, typically in the order of 200 instructions is what you can have sort of in flight at the same time. And these are not really instructions in flight. These are instructions, you know, from the oldest to the newest instruction. There could be a window of 200 instructions. You can imagine scheduling past branches and so on. You would have scheduled past quite a few of these branches to get up to 200 instructions. The issue queue, these are really the instructions that are more or less in flight. These are the instructions similar to the reservation station, instructions that you issue into that queue. Some of them are ready to go but haven't been scheduled yet. Some of them are waiting for the source values to become available. So a common size is on issue queue is about 60. This is a very, very complex design as well because of the associative lookup. Physical register file, well, typically if all the instructions in the reorder buffer needed a register, then you would need the same number of physical registers as you have slots in the reorder buffer. But since some of them don't need a register branch and stores, and this number is typically slightly smaller, so maybe 150 or so. 8 read ports, 4 write ports. Load store queue, same thing. If you have a program where you can have only perform loads and stores and nothing else, then you would then need the load store queue to be 200. But typically you make it smaller, maybe somewhere between 50 and 100 is the number of entries. These are very power-hungry structures. The issue queue may be the most power-hungry of them all. It's the associative wake-up. 4 instructions, 4 are completed per cycle, which means that all 4 of them must broadcast their sort of register identity here, and there could be 60 instructions waiting for that possibly could match any of those 4 completed destination registers in the very same cycle. Very power hungry. The physical register file is also power hungry, mostly because there are many read and write ports, also because the number of registers is quite high. Load store queue is also very power hungry. It doesn't look like it's doing much, but once more it's a very associative search. Every time you do a load or store, you have to search through this queue to see if you have any other outstanding activity for that very address, as well as every time there's a coherence activity coming in, you also have to search all those entries. And also the front end is very complex. It looks like it's rather boring. Just fetch an instruction, decode it, rename it. What's the big deal? But in order for this architecture to work well, you really have to be able to fetch 4 new instructions every cycle. Which means that you may actually, the very same cycle, you may execute 2 branches. That's of course they are predicted, so you do 2 branch predictions every cycle. For example, in some architectures, very complex to figure out which instructions to fetch, and there quite a lot of energy goes here. In a like a 70-watt server chip today, maybe, and I'm sort of guessing a little bit here, maybe 4 watts goes to the ALU, actually doing the real work, and the rest of all that energy goes to all the supporting troops that figures out where to get data, figure out which instructions to start when, and so on. So lots of complexity. So this is just showing a picture that we I think we looked at when we talked about the caches as well. So this is a screenshot of one of the Nehalem chips. So this is i7, one of the first i7 server chips with 8 cores. So the cores are in the perimeter here. And then we have the last level cache, which is tiled like this. So it's 3 megabytes in each tile, and it's a total of 24, if I get the numbers right, 24 megabytes of last level cache here. You have the QPI coherence links sitting up here. So if you magnify each core, see what goes in there, and it's a little hard to read on this slide here. Each core has an execution unit. Over here is instruction reorder, scheduling, and retirement. Well, we sort of recognize many of those words here. Instruction decode and microcode. So this is the translation. Memory ordering and execution. Okay. L1 data cache, L2 paging, branch prediction. We recognize that as well. Instruction fetch and L1 cache. Okay. So this is sort of the front end. You can say this is a cache as well, L1 cache, but this is also part of the front end over here. This branch prediction, you can view that as a cache as well, but it's more of a front end over here. You have the instruction decode, micro and microcode. So this is probably decoding, instruction, reorder, scheduling, retirement over here. And the execution unit is this space over here. This is a part of the chip that does useful work. The front end sort of here, these things together. The back end is this blob. Actually, you can view the L1 data cache as part of the back end as well, and this part over here. So it's of this chip, about half of it goes to last level cache, and of the area that goes to core, I would say maybe 1/6 of that chip is actually for the execution unit, and the rest of it is either front end or back end, or caches and the TLB, the paging system as well.